The farthest edge of our solar system is not empty at all. It wrinkles, flashes, and bends like a sheet in a windless room. You would expect the last border around the sun to be cold, still, and simple, but it acts more like weather than a wall. Stay with me, because this is one of those stories where the dark turns out to be crowded, noisy, and alive. And if you like science stories that make the universe feel close enough to touch, subscribe now so the next one lands in your feed before the mystery goes cold. For a long time, the outer boundary of the sun's world sounded almost boring. It was supposed to be a smooth bubble, a neat shell, the last breath of sunlight before true interstellar space began. Instead, scientists found a border that can puff outward, sink inward, glow in a ribbon across the sky, and even tilt off balance. It is less like the clean edge of a soap bubble and more like the skin of a living thing shivering in the dark. This boundary is called the heliopause, the place where the solar wind meets the gas between the stars. The solar wind is a stream of charged particles from the sun, and it blows for billions of miles, far past every planet you know. Out there, our whole planetary family rides inside a giant shield, and that shield decides how much harsh radiation reaches us. So when that shield ripples, or leans, or suddenly brightens, it is not just space trivia. It is the story of how our home survives. What stunned scientists was not simply that the edge exists. NASA has known that for years from Voyager and IBEX. What stunned them was how wrong some of the old pictures were, and how new maps keep revealing shapes nobody predicted. A place once treated like a quiet fence is now acting like a restless frontier, pushed from inside by the sun and from outside by the galaxy. And the strangest part is this: the farther we look, the less fixed that border seems to be. To understand this, we first need to go back a long way. Most people think the solar system ends somewhere near Pluto, as if the planets are the whole story. That is wrong, because the sun does more than light the planets. It blows a vast bubble around them. The planets are like furniture in the house. The heliosphere is the house. For years, the outer boundary had an underdog status in space science. Mars had dust storms. Saturn had rings. Black holes had drama. The heliosphere had no pretty surface and no place to land. It was invisible, huge, and easy to ignore, like the hum of a refrigerator you stop noticing until the power cuts out. But that quiet shield was doing one of the most important jobs in the solar system. It was standing between life and a harder galaxy. Scientists knew the basic idea. The sun throws out the solar wind, and that wind races outward until it starts running into interstellar material. They expected the far edge to look fairly smooth, maybe stretched by our motion through space, the way rain stretches around a moving car windshield. The actual boundary was supposed to be understandable with steady models, neat math, and a few broad curves. That was the expectation. A grand, simple bubble. Maybe odd in spots, but not shocking. The first surprise arrived in 2009, when NASA's Interstellar Boundary Explorer, called IBEX, started drawing the first global maps of the solar system's edge. IBEX does not take pictures the way a phone camera does. It reads energetic neutral atoms, tiny fast particles born in that distant clash zone. Scientists expected those atoms to be spread out fairly evenly across the sky. What they found instead was a narrow ribbon, almost a full circle, packed 2 to 3 times more densely than nearby regions. Imagine opening your freezer and expecting a smooth layer of frost, then finding one bright white stripe curled around the whole back wall. That is roughly what the ribbon felt like to researchers. Herbert Funston of Los Alamos National Laboratory said the maps looked completely different from what any model had predicted. David McComas, then at the Southwest Research Institute, said the first thing was simple. This was a big surprise. The numbers made it feel even stranger. The ribbon IBEX saw was brightest at about 1,000 electron volts, a unit of particle energy, and it showed up in a band between about 100 and 125 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the Sun, so a 10 astronomical unit change is like moving the whole boundary by 10 Earth-Sun gaps. That is not a wrinkle you ignore. That is like finding a fold in a blanket wider than the distance across your entire yard times millions. Scientists had expected the solar wind to be the main sculptor of that edge. Instead, the ribbon suggested the magnetic field of the galaxy just outside the heliosphere had much more control than expected. Nathan Schwadron of Boston University argued that the ribbon lined up in a way that pointed straight at that outside magnetic influence. So the first lesson was humbling. Our solar system does not shape its border alone. Another finding changed everything in a different way. Scientists expected one strange feature, maybe a one-time glitch in IBEX. What they found instead was support from another spacecraft, Cassini, which saw a broader belt of higher energy atoms in the same general part of the sky. It was like hearing the same melody on a second radio, but played in a deeper key. Cassini was out near Saturn, and it measured atoms above 6,000 electron volts. Ibex had seen the sharp ribbon at lower energies, from about 200 to 6,000 electron volts. Researchers expected the two views to line up neatly if the edge were simple. Instead, one instrument saw a narrow ribbon and the other saw a wider belt, which told them the boundary had layers. There was another clue tucked inside those early maps. Before Ibex, scientists had traced incoming helium well enough, but hydrogen and oxygen from interstellar space were much harder to pin down. They expected the solar wind to sweep the lightest atoms aside and hide the rest in noise. What they found instead were the first maps of neutral hydrogen and oxygen entering the solar system from beyond the termination shock. Stephen Fuselier of the Lockheed Martin Advanced Technology Center explained why that mattered. Hydrogen is common, but because it is so light, the solar wind can shove it off course more easily. During a very quiet phase of the solar cycle, more of those atoms slipped inward and reached the detectors. It was a bit like finally seeing dust in a sunbeam only after the room stopped shaking. At this point, what would you call that bright ribbon at the solar system's edge? A clue, a warning, or a complete surprise? Leave a comment because your answer helps me see which kind of turning point grabs you fastest in stories like this. That helps me build the next deep dive around the questions you actually care about. Then came the second surprise, and this one was even more personal because it came from two old machines still whispering from the dark. Voyager 1 and Voyager 2 launched in 1977, when Jimmy Carter was president and personal computers were barely entering homes. By the time most people forgot about them, they were still moving outward, like two sparks drifting away from a campfire that never quite went out. These spacecraft became the only objects humans had ever sent across that boundary. Scientists expected the Voyagers to confirm the broad picture, maybe with local details but no wild contradiction. What they found was a boundary that did not sit at the same distance in both directions. Voyager 1 crossed the heliopause in late 2012 at 122 astronomical units. Voyager 2 crossed in 2018.85 at 119 astronomical units. 3 astronomical units may sound small until you remember that 1 AU is the Earth-Sun distance, about 93 million miles. By then, the old image of a smooth bubble was already in trouble. The farther scientists looked, the more the edge behaved like a wrinkled shield in motion, and that shift in thinking opened the door to even stranger evidence. Those Voyager crossings also helped fix the scale of the story in human terms. The heliopause sits roughly 120 astronomical units out, or around 18 billion kilometers, about 11 billion miles, from the Sun in the directions those probes traveled. That is so far that sunlight out there is weak and thin, like the last gray glow left in a room after someone has already shut the door. And yet even at that distance, the Sun still matters. Its wind is still arguing with the galaxy. NASA describes the heliopause in very simple language. It is the distant region where the solar wind collides with the interstellar medium, which is the thin gas and dust between stars. Merav Ofer, a heliosphere expert at Boston University who has worked closely with NASA, has spent years explaining that this border is not a hard wall. It is a contact zone, a changing frontier, more like surf than brick. That matters because a lot of people hear the words edge of the solar system and picture a cliff. There is no cliff, no painted line, no cosmic fence post. There is pressure, motion, magnetic fields, and particles changing hands at insane distances. If you could hear it, it would not sound like a gate closing. It would sound like a long hiss, a low plasma hum, and then a sudden thinning of the storm. The third discovery grew out of a pulse from the Sun itself. In late 2014, spacecraft named ACE and WIND measured a large rise in solar wind dynamic pressure at 1 astronomical unit, right here near Earth. The Nature paper later described it as about a 50% jump. Picture turning the water pressure up in a garden hose by half and then waiting years to see the far end of the spray hit a fence miles away. That pressure pulse took time to race outward. Ibex, which maps the sky from near Earth, did not see the response right away. It began to catch the brightened signal in late 2016, first about 30 degrees below the nose of the heliosphere, then over wider regions later. The delay itself was part of the clue, like seeing a curtain move first at one corner before the whole window starts to shake. Scientists expected the outer boundary to shift some. They knew the Sun is not steady. What they found was much sharper and more dramatic. Eric Zernstein of Princeton University and his team used that 2014 event to build higher-resolution maps of the termination shock and the heliopause. On October 10, 2022, in Nature Astronomy, they reported ripples and oblique shapes that clashed with the simpler, steady models. The termination shock is the place where the solar wind first slows down hard, like traffic hitting a sudden jam. The heliopause is farther out, where the solar wind is finally stopped by interstellar material. The team found that the surfaces were not just moving in and out. They looked rippled, tilted, and asymmetric, with variations on the order of about 10 astronomical units. Let that size sink in for a second. A 10 astronomical unit ripple is 10 times the distance from Earth to the Sun, or far beyond the orbit of Saturn. In the ecliptic plane, the paper found standard deviations from roughly 3 to 10 astronomical units. In the meridian plane, a vertical slice through the heliosphere, the ripples ranged from roughly 5 to 16 astronomical units. Does it surprise you that the Sun's shield can ripple by distances bigger than Saturn's orbit? And if it does, will you like this video and tell me why? Liking the video helps the YouTube system notice that careful space stories deserve to reach more curious viewers. That simple signal gives this kind of science a better chance to travel. Scientists expected time changes, yes, but not this kind of wavy structure at that scale. What they found instead were boundary surfaces that looked oblique, meaning slanted, and in one big sense tilted about 30 degrees southward from the ecliptic. That is like discovering the roof over your house is not level after all, and some of its bends are wider than the whole street. The edge was not only breathing, it was leaning. By this point, the edge no longer looked like a clean shell at all. It looked like a giant moving surface, slanted and uneven, responding to forces we are still trying to measure. And once that idea sank in, the next mission suddenly mattered even more. And here is where the old picture really starts to fall apart. For years, many models pictured the heliosphere like a comet, with a rounded nose and a long tail behind as the Sun moved through interstellar space. Some later models suggested a croissant shape with two curved tails instead. The fact that both ideas survived tells you something important. Even now, scientists are still arguing over the outline of our own cosmic front porch. Ralph McNutt at Johns Hopkins Applied Physics Laboratory put it plainly in a later discussion of the problem. We know the boundary is about 120 astronomical units away, where Voyager crossed, but we do not know if it sits at the same distance in all directions. If it does not, then the heliosphere is not really a sphere at all. That is a funny thing to admit about the bubble that surrounds every planet, moon, comet, and rock in our solar system. The fourth discovery is really a new attempt to settle that argument. NASA launched the Interstellar Mapping and Acceleration Probe, or IMAP, on September 24, 2025, at 7:30 in the morning Eastern Time. It flew to the Sun-Earth L1 point, about 1.5 million kilometers or 1 million miles from Earth. From there, far enough from our planet's interference, it can watch the heliosphere from a clean seat in space. IMAP is about 2 meters wide, roughly 6.5 feet, and carries 10 instruments. That is not much bigger than a tall person lying down, yet it is trying to chart a boundary billions of miles away. NASA says it is a modern celestial cartographer, which is a fancy way of saying map maker. Like a person sketching a coastline by reading waves in the fog, IMAP will use particles to draw a border nobody can directly photograph. Scientists expected IMAP to sharpen the old map. What they hope to find may be much bigger than that. The mission aims to reveal the true shape of the heliosphere and track how its boundary changes over time, not as a frozen picture, but as a living system. Its science phase officially began in February 2026, and the timing could not be better. IMAP also turns the giant boundary problem back into human scale. NASA says the spacecraft can give about a half hour of warning for harmful radiation heading toward astronauts and spacecraft near Earth. Half an hour is not long if you are making toast. In spaceflight terms, it can be the difference between shrugging and taking cover. The spacecraft has a mass of about 900 kilograms, or 1,984 pounds. That is heavy, but not compared with what it is trying to understand. From L1, it samples material from the Sun, from the heliosphere's boundary 6 to 9 billion miles away, and even from interstellar space. A machine not much bigger than a bulky kitchen table is trying to read a border wider than the whole story of civilization. Dave McComas, the mission lead at Princeton University, has said scientists believe IMAP can finally resolve the heliosphere's shape. Martina Gakulidu, the project scientist at Johns Hopkins Applied Physics Laboratory, has said much the same thing. By measuring the energies and arrival angles of neutral atoms, IMAP may map the boundary out to roughly 300 to 400 astronomical units. That means a spacecraft near Earth could help sketch a frontier hundreds of Earth-Sun distances away. That is because the Sun keeps sending new instructions to the edge. Every burst in the solar wind, every change in pressure, every shift in magnetic structure can race outward and reach that distant frontier years later. It is like mailing a storm to the farthest room in the house, then waiting to hear when the window rattles. Except the house is our whole solar system, and the room is almost unimaginably far away. There is another underdog in this story too, and its name is New Horizons. Most people remember New Horizons as the Pluto spacecraft, the little piano-sized probe that gave us those famous icy heart pictures in 2015. But after Pluto, and after Arrokoth, it kept going. Now researchers at the Southwest Research Institute think it may become the third craft ever to reach the termination shock. On June 22, 2026, SWRI said 2 new papers used solar wind forecasting and heliosphere models to estimate when that crossing might happen. Jonathan Gasser, the lead author, said New Horizons could hit the termination shock as early as 2029 or as late as 2040. He even said it might cross that boundary more than once as the heliosphere expands and contracts. Imagine a door that does not stay in one place, but sways back and forth while you walk toward it for years. Who comes to mind when you hear that New Horizons may cross a boundary that moves while it waits? And will you share this video with them? Sharing helps this story reach people who would never think to look up the heliosphere, even though they would love it once they heard it. That is one of the best ways hidden science finds the audience it deserves. That line matters because it shows the boundary is not simply far away, it is dynamic. During solar maximum, when the sun is more active, the solar wind can turbocharge the heliosphere and push it outward. During solar minimum, the flow eases and the bubble can contract. It is like the difference between a lung taking a deep breath and letting it back out, except each breath spans years and billions of miles. The more exact the numbers get, the more personal the story feels. IBEX maps the whole sky every 6 months as it spins with a sun-pointed axis. The energetic neutral atoms it reads at the edge can take a year or two to reach the spacecraft from the outer heliosphere. So when scientists see a change in the map, they are reading a delayed echo, almost like hearing thunder long after the lightning has already flashed. And those echoes tell us something almost eerie. The boundary is not a dead shell. It stores memory. A solar event near Earth in late 2014 can leave a visible imprint out near the heliopause years later. That is like slamming a kitchen cupboard today and only hearing the loose plate rattle in the attic 2 winters from now. And there is one more reason this boundary feels so uncanny. The signals from it do not arrive in the order your instincts expect. A change near Earth can race outward, stir the edge years later, and then send particles back inward for another long trip. By the time the map brightens, the cause is already history, like seeing a porch curtain move long after the person who opened the door has gone inside. That strange timing is part of why this science feels so ghostly. The edge reacts long after the sun acts, so every bright patch in a map is also a delayed message, and reading delayed messages is much harder than reading a still photograph. There is a strange humility in the method itself. No one is circling the heliopause with cameras. Most of the picture comes from particles arriving like letters with missing return addresses. Scientists read the energies, the directions, and the delays, then rebuild the far edge the way a detective rebuilds a scene from a few muddy footprints. That is why the dates matter so much. IBEX shocked the field with science papers posted online on October 15, 2009. The strong solar wind pressure pulse arrived in late 2014. The brighter ENA response appeared in late 2016. Voyager 2 crossed in 2018.85. Then Nature Astronomy published the Ripple work on October 10, 2022, before IMAP launched on September 24, 2025, and began science in February 2026. Merav Ofer has spent years asking whether today's heliosphere even has the same shape it had in the past. That question matters because the sun moves through changing parts of the galaxy. A denser cloud outside, a different magnetic field, or a different solar cycle could all reshape the shield. It is the cosmic version of driving the same car through rain, fog, and snow, and getting a different pattern on the windshield every time. But scientists will tell you they do not fully understand this yet. That is not false modesty. It is the honest center of the whole field. The models had predicted something cleaner, and in several cases they predicted something different altogether. When the real boundary keeps showing ribbons, ripples, asymmetries, and timing effects, every neat sketch has to be redrawn. One reason this is hard is that no one can just fly around the heliosphere and take selfies from every angle. Voyager 1 and 2 crossed two tiny paths through an enormous structure. IBEX reads particles from afar. IMAP will do that in far greater detail. New Horizons may sample another region later. It is like trying to map an entire coastline from two boat landings, a weather balloon, and a handful of sea spray. Another reason is that the boundary is built by more than one force. From the inside, the solar wind presses outward. From the outside, the local interstellar medium pushes back, carrying its own magnetic field and its own flow. Where those meet, the edge can thicken, shift, bunch up, or flatten, the way two weather fronts can turn a calm sky into a line of rough clouds. This is why the old question, "Where does the solar system end?" does not have one simple answer. If you mean where the planets thin out, you stop near Neptune and the Kuiper belt. If you mean where the sun's magnetic and particle influence gives way, then you are talking about the heliosphere and the heliopause. If you mean the farthest loose grip of the sun's gravity, you keep going toward the Oort cloud, thousands of times farther still. That misunderstanding matters because it makes the real boundary easy to miss. People hear edge and think one clean finish line. But the solar system is layered, more like coats you wear on a freezing day. The planets are one layer, the solar wind bubble is another. Gravity stretches farther still, like cold you feel even through the door. The fifth discovery, if you want to call it that, is not one object or one date. It is the realization that the heliosphere is part shield, part signal, and part history book. Science News reported long ago that the heliosphere filters out about 90% of energetic cosmic rays, which are high-speed particles that can damage life and machines. So the shape of this boundary is not just a map problem, it is a safety problem. Which part of this whole picture hits you hardest now? The ribbon, the ripples, the time delay, or the idea that Earth lives inside a moving shield? Leave a comment because your answer helps me know which kind of wonder you want me to chase next. That helps shape the next deep dive more than any outline on my desk. Jamie Favors, who directs NASA's Space Weather Program, has pointed out that data from missions like IMAP can feed forecasts that matter for astronauts. If dangerous particles are heading toward the Moon or near Earth, early warning matters. The edge of the solar system may sound remote, but its physics reaches back toward our satellites, our spacecraft, and the people we hope to send farther out. It is a bit like checking the storm line at the far edge of town before deciding whether it is safe to walk home. And this is where the story becomes emotional, not just technical. For decades, the heliosphere was the invisible thing protecting everything visible. It never got the glamour of rings, volcanoes, or black hole art. But while we were staring at the bright objects, this dim border was doing the quiet work of holding off a rougher sea. The sixth surprise is almost philosophical. Scientists went looking for a boundary and found a behavior. They expected a noun, a thing, a place. What they found was closer to a verb, an ongoing action, a constant negotiation between the sun and the galaxy. By now, the picture was larger than any one discovery. The ribbon, the ripples, the Voyagers, and the new missions all pointed to the same truth. Our solar system lives inside a border that changes, remembers, and answers back. Think about the sequence again with the numbers in order. Voyager 1 crossed the heliopause in late 2012 at 122 astronomical units. Voyager 2 did it in 2018.85 at 119 astronomical units. IBEX had already shocked researchers in October 2009 with a ribbon no model predicted, brightest around 1,000 electron volts, and spread across the sky near 100 to 125 astronomical units. Then a 50% solar wind pressure rise in late 2014 helped reveal boundary ripples that Nature Astronomy published on October 10, 2022. That chain of dates is the sound of science getting closer. First the rough picture, then the old probes, then the global maps, then the sharper maps, then the next mission. It is like watching someone sketch a face in dim light, then add the eyes, then the mouth, then the scar you did not notice before. Each year removes a little blur, and each new detail makes the mystery feel more real, not less. If you could somehow stand near that boundary, you would not see a fence. You might see darkness salted with distant stars, a thin haze of charged motion, and the last scattered force of the sun pushing outward. You would feel no warm breeze on your skin, of course, but the idea of a wind would still be there, a pressure, a drift, a push against an ocean of interstellar gas. It would feel like standing where one weather system ends and another begins, except both are invisible, and both could swallow worlds. And somewhere inside that immense, restless border, Earth goes on with its tiny sounds. A coffee maker clicks on before dawn. A porch light burns. A child opens a fridge and stares at the glow. Meanwhile, far beyond Pluto, far beyond the Kuiper Belt, the sun's shield flexes by distances greater than the span from Earth to Saturn. The domestic and the cosmic are not separate stories. They are the same story told at two scales. At the start of this story, the edge of the solar system sounded impossible. How could emptiness wrinkle? How could a border appear to breathe? Now the surprise has flipped. The strange part is not that the boundary moves. The strange part is that we ever expected something made from wind, pressure, and magnetic fields to sit still in the first place. What once looked like a quiet line is now easier to understand as a living margin. Not alive the way a tree is alive, but active, responsive, almost musical in the way it answers every pulse from the sun. A burst near Earth can echo outward for years and show up in the maps like a note returning from a canyon. The farthest dark around us is not silence, it is delayed conversation. That changes the way the solar system feels. It is not just a collection of planets circling a star. It is a protected region with skin, weather, memory, and a constant argument with the galaxy beyond it. Few people wake up thinking about that shield, but all of us live inside it, every second, under its moving cover. And maybe that is the real resolution of the paradox. The most extreme boundary in the solar system is not extreme because it is far away. It is extreme because it turns distance into intimacy. A ripple bigger than Saturn's orbit can still matter to the safety of future astronauts, to the physics of our home, and to the story we tell about where we belong. So when you look up tonight, do not picture the solar system ending in a neat black circle somewhere past Pluto. Picture a vast, invisible shield, tilted, rippled, glowing in places, pushed from within by the sun and pressed from without by the galaxy. Picture two aging Voyagers beyond it, a new mapmaker named IMAP watching from 1 million miles away, and new horizons still heading outward. Picture the border not as a finish line, but as a restless shoreline. Because the truth we did not expect at the beginning is the truth we can carry now. Our cosmic home does not end in silence, it ends in contact. And somewhere in that cold, dark distance, the edge of the sun's world still trembles like a sheet in a hidden wind. Remember that the next time the night sky looks empty, it is not empty, it is listening.